I'm going to cover chapter 14 today, probably the whole chapter because it's a short one. And again, it's near the end of the semester, so we're going to talk real quick about solutions. Okay, a solution is a homogeneous mixture, and we've talked about that over and over again. You have one or more solutes and then dissolved in a solvent. And remember, when we're talking about solutions, it doesn't just have to be a solid dissolved in a liquid. You have gases dissolved in each other, like air. You can have two solids, like alloys, the things that we make our jewelry out of. So there's all kinds of solutions. They're not just a solid, excuse me, dissolved in a liquid. When you're making a solution, though, the stuff, whatever is dissolved is called a solute. Whatever does the dissolving is a solvent. So if I'm making a salt water mixture, salt is the solute and water is the solvent. Okay, if I'm making like pop, you have carbon dioxide dissolved in water. So the solute would be the gas, carbon dioxide, and the solvent again would be water. Most of the time the water is a solvent. Water is a solvent probably 90% of the time. That's why they call water the universal solvent, because it dissolves more things. Okay, and again, remember, a solution doesn't have to refer to liquids. We talked about it. Air is a mixture of nitrogen gas, oxygen gas, argon, carbon dioxide, water vapor, all kinds of things. So it just, anything that's well mixed together is a solution. And I know it sounds weird that air is a solution, but it really is. Okay. Okay, so soda is a mixture of sugar in water. So what would be the solute? The sugar. What would be the solvent? Water. And now, soda is kind of funny. Soda. Who says soda? Pop is also got another thing dissolved in it, carbon dioxide. So you actually have two solutes. You have carbon dioxide and you have sugar. Okay. Here it says a solution is prepared by adding 25 milliliters of ethyl alcohol to water. Again, which one is the solvent? It would be the water. Which one is the solute? It would be the ethyl alcohol. Okay, so again, whenever you're making a solution, you have a solute and you have a solvent, and together they make a solution. Okay, here's common types of solution. Two gases dissolve. You have air, a gas dissolved in a liquid, pop. A liquid dissolved in a liquid, like antifreeze. You have a mixture in your car. A solid dissolved in a liquid, salt water. You can have a gas dissolved in a solid, like hydrogen and platinum. It gives it like a coating on it. And you can have two solids dissolved. Those would be alloys like brass, okay, stainless steel, things like that. Okay, so whenever you're talking about a true solution, though, it's a homogeneous mixture of two more components, and the ratio can be varied. That's how you know it's a mixture. If I'm making a salt water, I can add a pinch of salt, I can add a tablespoon of salt, I can add a cup of salt. I can change the amount, and I can put it in, a glass of water. I can put it in a big 2-liter bottle. I can put it in a gallon. You can change the components, so that's how you know it's a mixture. Okay. If it's a solution, the particles, when they dissolve, are less than 1 nanometer. They're so small that they don't affect. You can't see them. If you put them under a microscope, there's no way you'd see them. So whenever you have a solution, a true solution, the particles dissolve to the point where you can't see them at all. Okay. They can be colored, like Kool-Aid. Kool-Aid, you have a solution, but most of the time they're transparent. Not always, but most of the time they are, okay? The solute remains dissolved and doesn't settle out. So if you see particles settling out on the bottom, and this can happen with a saltwater solution if you add too much salt, but if no particles settle out, then you know it's a true solution, okay? And you can separate them again. If you make a solution with solute and solvent, if you use a physical means, like usually it's evaporation. If I make a saltwater solution, I want to get my salt back, I just boil off the water and then I get my salt back. So a solution, a true solution, you can get the particles, you can get your solute back, okay? And there's no settling, the particles are very small, okay? So if you're looking at, they have a thing called solubility. And solubility is how much solute can you dissolve? Because there's a limit, okay? I can't just keep adding salt to water. Eventually it'll get to the point where it doesn't dissolve anymore. And if you increase the temperature, usually you can dissolve more. Here's an example of potassium bromide in water. Okay, at 23 degrees, it doesn't dissolve anymore. Okay, but if I increase the temperature, then maybe I can get more to dissolve. Okay, there's a term that you use when you're mixing two liquids together. Okay, it's kind of like soluble and insoluble. But for liquids specifically, if you take two liquids and you mix them together, like if you mix alcohol and water and you mix them together, you can mix them and mix them and mix them and mix them and mix them. and they will continue to mix. There's no, set amount. If it's immiscible, it's where they don't dissolve. Here they're showing putting oil in water. Oil and water don't mix. So they're immiscible. And again, miscible and immiscible only deal with when you're mixing two liquids. There's soluble and insoluble, which is kind of like miscible and immiscible, but soluble and insoluble is for all substances, a solid and a liquid, two solids, whatever. Miscible and immiscible are only for liquids. Okay, here's a mixture of water. Like I said, these are immiscible because they just won't mix. You can shake them all you want. They'll still separate. Okay, when you're looking at whether things are soluble or not, there's a term called likes, dissolves, sorry. Likes, dissolve, likes. And what they're talking about is their bonding type. So if you put two polar covalent substances together, they'll dissolve each other. If you put a polar and an ionic, they're going to dissolve because you've got those charges. If you put a polar with a nonpolar, they're not going to dissolve each other. Okay? So likes, dissolve, likes, when they're talking about that, it's a way of determining if two things will actually dissolve. And again, it's based on their bonding type. If you put two nonpolar together, they'll dissolve each other. But if you put a polar and a nonpolar, they won't. Okay? So nonpolar dissolve nonpolar solvents. Okay? And again, this is carbon tetrachloride. It's one of the things they use in dry cleaning. Okay? But they'll dissolve. But if you put carbon tetrachloride in water, because water's nonpolar is polar and carbon tetrachloride is nonpolar, they're not going to dissolve each other. Okay? So ionic compounds, they are very soluble in polar solvents. Again, that's why water's such a great solvent, because it's polar. And again, the reason is you've got positive and negative ends. In an ionic compound, you have positive and negative ions, so they just, are attracted and they tend to pull things apart. The individual cations and anions are surrounded by water. They call that hydrated. And now the cation will be attracted to the positive end, will be attracted to the negative oxygen, and the anion, which is the negative, will be attracted to the positive hydrogen. So they do a really good job. You can't see it very well down here. This is like salt. And what happens is the water just kind of like, Pac-Man's its way in there and chews these guys and separates them out. It doesn't really chew them, but you know what I mean. Okay. You can tell this is a chart that's been developed to help you look at solubility versus temperature. You'll see these all the time. But what it does is if you look here, let's say I want to know if I got potassium nitrate. Okay, I want to know how much will dissolve in 40 degrees. So all I have to do is go like here. If the temperature is 40 degrees, 70 grams of potassium nitrate will dissolve. And this is in 100 grams of water. Okay, you can also look at their charts and see, okay, potassium nitrate as temperature increases really becomes more soluble. Sodium nitrate is pretty soluble at all temperatures. Even when the temperature is 0, look how soluble, you can get 70 grams dissolve. Okay, some of them, like, look at salt. Salt is almost straight across. So when you increase the temperature, it really doesn't increase the solubility of salt. Okay, here you got sulfur dioxide. It actually decreases. Okay, that's rare, but it does happen. But again, you can look at, these are solubility curves, and it can tell you by looking at this chart. I say, okay, how many grams of ammonium chloride will dissolve when the temperature is 90 degrees? So I go, 90 degrees, about 72 grams. So that's what a solubility curve tells you. And this was determined all through experimentation. Okay, so solubility increases with temperature for most solids. Okay, the blue lines are gases. Okay, gases actually decrease because what happens is if you increase the temperature, the particles move so fast they just escape. So their solubility actually decreases when you increase the temperature. And that's why warm water has less oxygen in it than cold water. Fish like cold water. It has way more oxygen in it. When the water gets heated up, then what's going to happen is you're going to end up with not very much oxygen, and the fish aren't going to do very well. So cold water is better because it has more oxygen in it. Okay, so as a gas increases in temperature, the kinetic energy of the particles, they're moving so fast, they basically just escape. So now you don't keep them dissolved. So these two are gases, and that's why they decrease. Okay, and gases always decrease as you increase the temperature. But most solids dissolve in liquids increase. Okay, pressure does not affect solubility of liquids or solids. It doesn't affect, but it definitely does in gas. And we did that. Remember, we did the gas laws. But the gas solubility is proportional to the gas pressure over the liquid. The colder it is, the more you can get to dissolve in it. Okay, that's why there's more fizz in cold water, cold pop than warm pop. Okay, here's a bottle of root beer. It's under a certain pressure. Once you release that pressure, you open it up, the bubbles are going to escape. Okay, you're going to lose gas from that liquid. If you want to keep them in there, you got to keep the pressure on. Okay, so, and again, that's why there's way more carbon dioxide in fountain pop than there is in bottle pop, because there is no way to hold it in. The pressure, there's no container. You don't have a lid. You have put a plastic lid on your pop, but it really doesn't keep the gas in. So pressure affects solubility. The more pressure, the more stuff you can dissolve in it. Okay, there's stuff called saturated and unsaturated solutions. Okay, there's a limit to how much stuff you can dissolve. At a certain point, when you've gotten to the point where no more will dissolve, like I'm making a salt solution and I add a little, I stir it, it's dissolved, I add a little bit more, stir it. At a certain point, I'm going to add it, it's not going to dissolve. That's saturated. And on that chart I showed you, it would be above, like I showed you, 90 or 73 grams will dissolve at a certain temperature of a substance. Well, if I'm above that, those solutions are saturated. They can't dissolve anymore, okay? So saturated is where they've reached their limit, they cannot dissolve anymore. Unsaturated is when you can still add stuff and it'll still dissolve, okay? So unsaturated, the solutions start out as unsaturated. As you add more and more solid, they become saturated, which means that's it. I won't dissolve anymore. This is it. I'm done, okay? There are some super saturated solutions where you could get more solute in than normal, and usually that's because you raise the temperature pretty high. A common thing, if you ever made like crystals, those crystal gardens and stuff, those solutions are super saturated. And when they cool back down or when they come out they form crystals. And usually the crystals are kind of cool because they're bigger than normal. Okay, we used to do it with borax. We put it on pipe cleaners and you get all kind of pretty crystals on them. But not all solutions allow you to be super saturated. And usually it's because you put it at a really high temperature, you dissolve a bunch, and as you cool it down, then you get really big crystals. It's kind of cool, actually. Some hot packs use that. But the solutions, again, when you super saturate them, they're not very stable. So they're going to precipitate out the solute. And again, usually in really big crystals, so it looks kind of cool. Okay, so here's a solubility practice. You'd have to go back to that chart. Will a solution prepared at 9 grams of potassium chlorate in 20 grams of water be saturated or unsaturated? This is one where you'd have to go look at that table. Okay, and again, I'm not going to worry about that, but the table is a table like that. You'll see solubility curves like that all the time, and it's just matching at what temperature, finding your substance, and determining whether it will be saturated or unsaturated. Saturated means it's dissolved all it can. Unsaturated means you can dissolve more in it. Okay. When you're looking at dissolving solids, the particle size makes a difference. Obviously, the bigger the particle, the harder it is to dissolve. So when we have big particles, we try to smash them into smaller particles. If we can make them smaller, they'll dissolve faster, and that's called making it a higher surface volume ratio. In other words, there's going to be more contact because you've crushed it down into smaller pieces. Okay. Temperature, when you increase the temperature, the rates of dissolution happens faster because, again, you're exposing more water to the particles because they're moving faster. The particles are moving faster. They're exposed to more things. They're going to dissolve faster. Okay. The solvent strikes the solid surface more rapidly, and it'll cause it to dissolve. Okay. And then with a more solute concentration, here you have the rate, the highest concentration obviously is up here is where it's saturated. See how it doesn't change anymore? I can add more, it's not dissolving. Okay, so this increases the concentration of the solute. When you have lower concentrations down here, then it's going to dissolve at a less rate. Okay, so as the solution approaches saturation point, now it's not going to dissolve anymore. Okay, here it's dissolving, it's dissolving, it's dissolving, it's dissolving, and now it's not when it gets up to here. It's reached it just can't dissolve anymore. That's it. It's reached its maximum point. Okay, ways you can increase it. You can stir it. That's called agitation. Oh, boy, that went quick. Let me see. We'll go back to this last one. Okay, so if you want to make a solution occur faster, you stir it, you increase the surface area, you crush it, or you increase the temperature. That's the way you can make solutions happen faster. And that's the end of our notes.